the take home, but let's do a couple examples first. So on Monday, this thing is messing me up. Last week, we did MM3. We did one example, and we've really only done that one all the way through. So let me do one more of those, that type. So let me make it MM4. With lambda equals 3 and mu equals 1. And so part A will be to find the steady state probabilities. And then the follow-ups will be to find the even and even Q and E of T and E of W, and then find the CDF for W, and then question for how long we might have to wait in line. So pretty much most of what we did on the one example on Thursday. So here we're back to one where lambda is fixed. Those are all supposed to be 3s. And the first one, mu is equal to 1, so therefore this is 1. And now you're just going to tell me what the next few are. What are each of these, let's say 4. What are each of these next 4? What numbers do I get? Yeah, so 2, 3, and 4. And then the next one would again be 4. So I stop there for a second and ask, are there any questions on any of these? And then we don't need any more of this because it starts being 4. Oh, so the reason the last one is 4 is because we're doing MM4, so therefore the maximum is 4 servers working, each at a rate of 1, so therefore that's the maximum of 4. So once we get past 4 people, it is a maximum. Okay, so start putting in the different ones. So what is, do a couple of these and I'll fill out the rest. What is P1 in terms of P0? So what's the number in front of P0 there? And same thing here. What is the number in front of the P1? And then I'll just do the rest. So the ratio in front of from P2 to P1 is 3/2. Yep. That's supposed to be a 3 over 2 there. And then 3 over 3 and 3 over 4 and so on. Oops. And I kind of ran out of room, but it works out okay because once I've gotten to this one, from now on, I'm just going to keep multiplying by 3/4. And so now we're going to add them all up, set it equal to 1. So obviously I have to go on the next page. So any questions on this before I erase? Okay, so let me erase. And I think I'm missing one. No, I'm not. Never mind. There are 2 9.5s. Sorry. Now, as I said last week, we could get a actual formula for this, but for me, it's just easy to see that this eventually becomes geometric. So which of the terms does the geometric start with? First, second, third, fourth, fifth term, which is the first one in the geometric part? So fourth, right? Because you get third. So this is the fourth one. Because to go from the third to the fourth, I multiply by a half, but then I multiply by 3/4. This term is to be 9 over 2 times 3/4. So therefore, starting here, we keep multiplying by 3/4. So this part, and in some ways you can see it, we have MM4, so it starts being geometric with the fourth term. So the sum of these is, again, depending on which way you do it, first term, the A over the 1 minus R, which is the 3/4. And then the 18 plus the 1 plus the 3 plus the 9/2 I get is 53 over 2. So 19, 22. Does that make sense? So it's 21, 22, 44, yes. And then we can solve. Using the formulas from the last one. And for these, I will ask you to get it through through PC. So here's MM4, so we go through P4, and that's because the next part of the problem, where we get E of n and E of n q and so on, P of 4 is in the formula. So the denominators for the first 4 of these are supposed to be 53. So any questions on any of these? So this specific one is one we'll use in the next part. So I'll ask here and I'll actually do on the next slide. So we want to find these 4 things. And again, remember that 2 of these are the totals. So this is the total number of people in the store or system. This is the total time you're in the store or the system. Whereas these 2 are instead in terms of the line. So first one is the number of people in line. and this is the time you wait in line. There's two other ones that are sort of in the background, which in terms of how many people are at the server and how long it takes you to be served, but those are fixed, so we don't worry about getting those. So this is what we're going to get in the next slide. So any questions on this before I move on? Okay. So since these are infinite, the one we did Thursday, this one, MM4, we don't really want to do it the direct way, 0 times P0 plus 1 times P1 and so on. We want a formula. And for MMC like this one, this is the formula we know, which is in terms of NQ. Rho, remember, is lambda over mu, but really you can get this directly. The rho over C is the R in the geometric part, so it's the 3/4 that we got before, which is lambda is equal to 3, mu is equal to 1, C is equal to 4. Therefore, we get this, the 3/4 divided by the 1 minus 3/4 squared times P of 4, which we found was 27 over 212. I get that is this. As always, you're checking my arithmetic. So mu is 1, but C is 4. So I'll put them all in. This is 3, 1, 4. Okay. Given this, which one do we find next? So we now have E of NQ. What's the next one we found last week? So we have the three other ones. We have N, W, and T. Which of those do we need to do next? W. Yep. Because Little's theorem equates the two. So by Little's theorem, E of W is equal to 1 over lambda E of NQ. And obviously we now know NQ. We know lambda is 3. So we get that. And then from this one, what do we get? So we got E of W. Now we get E of which one? T. Okay. Because we know, again, a formula. That T, the total time we're in the system, is the time we wait in line plus the time it takes to be served. For us, the time to be served is always exponential with mu, and we know the expected value for an exponential with parameter mu is 1 over mu. And again, mu here is 1. So I add the 1 to W. I get that. And then, of course, the last one I get is E of N, which is, again, Little's theorem. So I get the 4. As I said last week, if we really wanted to, we could solve these in general. So for example, to get E of W, we're dividing by lambda. So if I go to my formula up here, well, I know that rho is equal to lambda over mu, so I could cancel out one of the lambdas and make it 1 over c times mu. But for me, I find it easier to just remember it separately, but whichever you'd rather. So if you want, you can make formulas for the rest. So these are all the numbers. Now we want to deal with time. So we want to get the CDF and sort of, here we won't need it, but just to remind you what you do for the take home, the PDF for W. So any questions on this? Okay, so let me erase to part C. Oops. So remember, in terms of getting E of T, mu does not change because for the time to be served, I don't care how many servers there are because I'm only being served by one person. So once I'm being served, mu is the fixed mu that's given at the beginning. So let's find the probability that the time we wait in line is more than 2. So on Thursday we did less than, here we'll do more than. We need 2 parts for this, just like the one on Thursday. We need what is the probability that time is equal to 0, which is, how far does that go? So we start here, P0 plus P1, and what's the last term? And for this one, you have to remember what we're asking here specifically is, I'm going to the store. I want to know what's the probability I have to wait more than 2 minutes, hours, whatever the time period is. So certainly if I get there and there's no one there, I don't have to wait. Certainly if I get there, there's one person, I don't have to wait. So as I said, what's the last one that's going to be in it? Oh, I think you went the opposite way. So if I get there and there are 2 people there, then that means, so 3. Because if I get there and there are 3 people there, 3 of the 4 servers are working, 1 is free, which means I'm going to get there. Whereas if I get there and there are 4 people there, all servers are busy, I'm going to have to wait. So looking at what we had before, I thought that this was, and as always, you should double check, the sum of those 4 was 26 over 53. The other thing I need is the conditional density function, or CDF, that we got last week. And so we have a formula for that. Yeah, let me rewrite it since I messed up. And again, there are a couple ways of remembering it. So this is one formula, but if I multiply it by the C mu, then the C's will cancel. Rho is lambda over mu, so the mu will also cancel. And I'll get that. So whichever of those 2 formulas you would rather. So in this case, what does it give us? So negative C times mu plus lambda is, and from the previous one we had lambda was 3, C was 4, and mu was 1. So we get a really simple one. So putting putting it all together, we get a mini tree. So unlike the one we did Wednesday where we had the two pieces, we can be more than two only in one way. We need that we have to wait in line, and then we have to wait less than 2 minutes or hours. So now we plug in the different things. So the probability that W is more than 0 is the 1 minus the 26 over 53. And I, for some reason, switched this. This should, of course, not be... Usually someone would have noticed this before me. This, of course, shouldn't be less than. It should be the same as that. That should be more than. So the CDF gives us the probability that we're less than whatever number we plug in. So to get the probability that we're more than it, we subtract it from 1. And I get that. So the W is more than 2 comes from this, because I asked for it. Right, but the idea is that this is conditional. It's only the probability if W is more than 0. So typical tree thing, we have to say, well, first it's more than 0, and then it's something else. Because it could be that we just don't wait in that line at all, and so we have to drop that off. And that's supposed to be a 27 over 53. Okay. So we did one of these on Thursday, except did less than. With less than, of course, we'd have had a second piece where it would have been the probability W is equal to 0, plus the probability that W is less than, is more than 0, and still less than whatever the number was. So I'm not going to do the full thing because this is the take home, but let me ask you the easy thing, which I'll bring to the next slide. So before I do, any questions on this? So I won't do the whole thing, as I said, because we did one Thursday, but let me ask, what is this? And then how do I at least start the next part, which is getting T? So first, what's the relationship between this and the CDF that we got? So how do I get this, the PDF, given the CDF? Right, so the derivative. So here, the CDF was 1 minus e to the negative x. And I'm not sure why I'm making that x. Sorry. It's a fairly simple one. Here we didn't use it, but you will on the take home. What is the PDF for the time it takes to be served? So in the background, we assume it's exponential, because remember from the beginning, we assumed that things were exponential, that the arrival rate was Poisson and the departure rate was exponential. So the only question here is, what is the parameter for this? So in other words, what is the number of my blank, which it's the same for both of them. this case the 4. No, sorry, 1. Thinking of C. And then finally, how do I get the density function for T? And the one thing you need to do this is we're assuming that S and W are independent. So therefore, how do I get T? Yeah, so just the product. And then if I want to find what's the probability that T is less than 1, well, that's the sum of S and W, so I'd have to draw the picture, do the double integral. So there's our joint density. So I'm not going to go further, as I said, because this is take home. But any general questions about this? Oh, so we will when we put it together. So we did that Wednesday, right? Because we said the probability that T is less than 0 breaks into 2 pieces. Part of it will be, so here, yeah, this is mixed. This really is a conditional type thing. F of T given W is more than 0. And then there's going to be a second part. What is F of T? This is W more than 0. And then there will be a second. So officially it's, which is what we did Wednesday. It's going to be this 2. And if W is equal to 0, then of course we don't need the W, and it's just the surface part. So what's the purpose of the derivative? Oh, so it's just the formula that we have, the CDF, the cumulative distribution function, but to do, which we use in the last one, but in terms of the problem you're doing in the take home, in terms of T, we need the PDF, and the PDF is the derivative of the CDF. So right, so this is mu e to the negative mu s in general. That's supposed to be mu there also. So any other questions in this general part? So Wednesday, we can be more specific about some of this stuff. So, right, so we did S plus W is less than 1. So I think we did. Well, we'll talk Wednesday, we'll talk more specifically about this because you'll just be working on the take home. Yeah. Sorry. Give me a second. My screen got messed up. Okay, it's back. So yes, on Wednesday, you can ask more specific questions, but for now, just kind of general things on this, what we've written so far. All right, so the other thing I want to do is we also haven't done many finite ones, especially I think we've only done one where lambda wasn't constant. So let me do one of those, and I'm going to make it different just to confuse the issue a little bit, but keep it similar in other ways. Lambda is the arrival rate. So in the story, you say it or something like that. So let's suppose we have a variable arrival rate. So this to be something that might come up for tickets or something like that. So the more people are that are in the store, the more people want to go. So the more people are there, the more people want to be in. The difference between this one and the one we did Thursday is the one we did Thursday, I made n be the number of people in line. Here instead, n is the total number of people in the store. So again, it's correcting my writing. So both these are in minutes. So this is the arrival rate, number of people per minute. And we have two servers who can each serve one person per minute. And again, I want to get the steady state probabilities and then E of n and E of t and so on. So here I'm going to draw it here. And this one we'll have to figure out how far we go. So I'm not sure if I'll actually go that far. So this one is just reading off, unlike the last one on Thursday where we had to rewrite it. So it's 0, n is 0, and therefore their arrival rate is 1. At 1, n is 1. Again, we don't have to change anything. So therefore, the arrival rate is 4/3. And then n is 2. N is 3. And then n is 0 otherwise. So therefore, this is 0, which means we don't have anything beyond it. So I said different than Thursday, where Thursday was the number of people in line. So you had to shift things over. This one, it's one person server can serve per minute. So this is 1. On the other hand, what is this? And then from there on, it's, so this one is also 2 and 2. So we get this. So here, let me write the relationships and again, go to the next page to actually solve it. So here, P1 is equal to P0. So the first one is 1 because of this. We have two servers, but there's only one person. So at this point, there's only one person in the store, so only one of them is working. Whereas once I get to here, 2 people are working, so now both servers are working. So there are my relationships. Since I just wrote that up quickly, let me give you a minute to both see if you have any questions and check my arithmetic. This is supposed to be a 2. And again, you can, I don't know if you can see it as I'm writing it, but as I write it, it will smooth it out, which I don't want it to do, but I'm not sure how to change that. So that's supposed to be a 2/3. So first, are those okay? And any questions on how you get any of them? This we've now done a bunch of times, so that should be okay. But any questions on how you get any of these? Okay. So there, 4. So the sum of the 5 probabilities, pull out the P0, and you have the 1 plus 1 plus 2/3 plus 2/3 plus 4/3. So that is up to 14/3. So P0 and P1 are the same. About 3/14. P2 and P3 are also the same. They're both 2/14 or 1/7. And P4 is 2/7. And again, we want to find all the different ones. So E of n is again the easy one. Here, I don't give you a formula because this one you can just use since it's finite. Obviously, you don't have to write that first term. Just the usual expected value times probability. I got 29/14. E of nq we can again get using the basic thing, but now we have to shift things over, which is where do we start? So where's the first one that we're not multiplying by 0? So obviously at 0, at P0 at 0, at P1 is also 0. What's the first one that's non-zero? Yeah, so P3. So we're going to have 1 times P3 and 2 times P4. And I said this last week, but let me say it again, which essentially what we're doing is, since we have 2 servers, we're taking the number of people and we're subtracting 2, except of course you can't get less than 0. So if there's 0 people there, then obviously there's no one in line. If there's 1 person, then if you subtract 2, you get 0. 2 becomes 0. 3 becomes 1. 4 becomes 2. So you get that. So for this one, now for 2 reasons, we can still use little's theorem, but now we need this thing I'm calling lambda A, which is the average lambda, because there is no single lambda. And so we're going to do something similar to E of n, which is we're going to multiply the rate at the state times the probability of the state. So looking at the graph from previously, what is in front of the P0? So here, what are the coefficients? So the rate going in to the graph from what I had before, the rate going in if there's no one in the system is the 1. Sorry, again, it's being weird, so give me a minute. And at P1, it was 2/3? No, 4/3. Right. At P2, it was, I think, 2. And then 4 at P3. And at P4, it was 0. So first, before I do anything with this, are those numbers correct? And similar question, any questions on those numbers? So first, are those numbers correct? Those should be the numbers across the top of the graph that I erased. Is that true? Yep. Okay, so any questions on why we get this? So I got that is 19 over 14. And now we can use Little's theorem. And it doesn't matter which one we start with. So we can now get E of t, we can get E of w, whichever you'd rather. So I get those. And in some ways, the nice thing about the finite ones is we have a second way of relating the t and w. So we have a way of double checking to make sure we haven't done something silly, which is we know this is true. I know that mu here is 1, and we get that this does work. So we've kind of double checked things, that we haven't made a mistake in doing any of the other parts. So this is the second type of example. This one, remember, we don't do time. We don't try to get the density function. We tried it for 1, but what happened is we're going to get an exponential times a polynomial, because that's not going to simplify. In this case, because we had 4, 4, it would be a 4th order polynomial, a quartic, times the exponential, and we really don't want to use that. So in theory, we could get it. In practice, you're not going to get it because it's just very tedious. So any questions on these? So this is as far as we go with this type of problem. Yes, whenever mu is 1. Any other questions? So in some ways, that's the end. So you can kind of see why Wednesday we're going to do the, so mu is 1. That was from the beginning. We said each server can serve 1 person per minute, which gave us that mu was 1. So that has to be given to you in some form. Any other questions? No problem. All right, so as I said, this is kind of the end of Qs, which is why Wednesday you're just going to come and going to work on it. But I'm still going to do the quick intro into the next thing. In the notes, we next do some technical things, but I'm going to skip that for now, and we'll come back to it if we have time. Different arrival rates and exit rates. Yes, yeah. So as I said, Wednesday is going to be completely open. So I will come in. It'll be like office hours, except hopefully a lot of you will come up, and I might try to form groups so that you can talk amongst yourself, and then I'll go in and answer questions. And if that's doesn't work too well, I also have the office hours that you can come by. Okay, so any other quick questions? Okay, so let me do the usual quick intro. And here for 2 reasons. One is it's not in the take home, and so we won't get to it again until Thursday. And the other is some of you, this will be really basic, and some of you might have seen this because we're going to get into stock stuff. So I do an example. and talk about it quickly. And then I said, we'll come to a question which we'll start answering later. So first, to get the idea down, we're doing something really simple. So we have a stock that currently is worth $10, and in the future, it's either going to be $5 or $50. To make it simple, we're going to assume that time doesn't really exist. So either it changed to $5 or $50 and then we're done. And we also assume that there's no inflation or anything like that. So it's just purely this now and next to keep it nice and simple. Besides that, we can also buy what's called an option. So there's an option to buy the stock for $20 in the future, which is basically a contract. You pay someone a certain amount of money, and with that contract, they will sell you the stock for $20 in the future, no matter what the real price is. So if you think the price is going to go up, you're going to buy this option because then you'll be able to buy it for them for $20 and then sell it immediately for $50. So the question is, how much should we charge for the option? Obviously here it's a bit silly, but we're going to start with this, then we're going to, which lets us consider the case where the stock goes up and down continuously and ask the same question. So we're getting the idea using this really simplistic model, and then we'll make it more complicated. So sorry. So just to give them numbers, let C be the price of the option, which we don't know right now. Let X be the number of stock we're going to buy. Let Y be the number of options we're going to buy. And since we can buy and sell things, both X and Y can either be positive or negative. Just arbitrarily, let's say positive means you buy the stock or option, and negative means you sell the stock or option. So let's get some equations. So if I did buy X stocks and Y options, and the stock went up to $50, then how much money do I make in that? So assume that if it goes up to $50, I will sell and make whatever I make. So for example, the more obvious one, for each stock I buy, how much money did I make? To the 40, because it was $10, now it's $50, I made $40. And the slightly more confusing, what about for options? So here what's happened is the stock went up to $50. I use my option to buy it for $20. I immediately sell it for $50, but I paid C dollars for the option. So this is I bought it for $20 from the person with the sold it for $50, made $30, but I have already given that person C dollars. So that would be my equation. And they do the same thing. What happens if the stock goes to $5? Then for each stock I bought, I now obviously lose money. So for each stock I bought, I lost how much? Again, the more direct one, hopefully. It was $10, now it's $5, so I lost $5. This one, again, if you haven't done it before, you have to think about it a little bit, which is if I bought the option to buy it for $20 for $50, if the stock goes down to $5, how much money do I lose? I shouldn't really have the plus there because it's going to be negative. Right. And the idea here is I'm just not going to use the option because the option says I can buy the stock for $20, but I'd be silly to do that because I can buy it from anyone else for $5. So I just lost whatever my investment was. So obviously I said we have to do more, but let me bring this to the other page, just bring the equations over and notice that we have a particular type of problem here. So any questions on this setup? So these were the two equations we got. It's only arbitrarily put in a number for C. Let's suppose C was $10. So now the two equations are these two. And these are the net amount I make. And now I notice if I let x be 10 and y equals negative 10, then the top equation is $200 and the bottom equation is $50. And the important part is both of those are positive values. And that's bad because that says there is now guaranteed money. So if I make this bet, and of course I use 10 and negative 10, but any multiple will still work. So 1,000 and negative 1,000, I can make as much money as I want. And this is called arbitrage. Which I'll talk about on Thursday. Which is arbitrage is just a betting scheme that is guaranteed to make money. And those are always kind of bad in things. So this, in this case, if I let C be 10, there's a bet that's guaranteed to make money. Why? That means, so here I'm assuming that I can buy and sell. So if positive is buy, then negative is sell. So this is saying I'm going to buy 10 of the stocks and sell 10 of the options. So I can both buy and sell both these things. Okay. So, as I said, this is kind of bad. So the question is, which is the question for the people running the businesses, because arbitrage is bad. So the question is there value of C so that there is no arbitrage? And if there is, that is what we'll charge for the stock. So this one we'll see there's a fairly easy way of solving for it, and there is a particular value of C. And then, as I said, then we'll make it more complicated by saying that price of the stock follows a Brownian motion type thing, which is randomly going up and down, and ask the same question: is there value of C that prevents there being arbitrage? And so that's where we're going with it. And officially, if the people in finance or economics, that means we're going towards what's called the Black-Scholes equation. Really simple version of it, because we don't have time to do the full thing. Also, we're going to partly prove it in a simple way, because the full thing is this really is a set of partial differential equations that we're getting, but we're going to pretend it's not. We're going to keep it simple. Okay, so let me stop there. As I said, Wednesday is just look at, figure out who you might be working with, and do enough so you know what your questions are for Wednesday. And Wednesday, as I said, I'll probably be Zoom, but I'll put out an announcement where you'll just come in, I'll be there. I'll probably put you in different breakout rooms, working together. Then I'll go into the rooms when people have questions. And have a board like this so we can write to each other. So I'll make it so that you can also write on the boards so I can see them, hopefully. So any questions before that? Okay. All right, so let me stop recording, but again, the usual thing, I'll stay for a little time if you have more specific questions.